Hi, everyone. Welcome to my channel. There's a lot of confusion out there in Flerfs world about density, buoyancy, and gravity. So I decided to make a little video about it and hopefully clear it up. First thing I've done is what we're going to do is we're going to take an object. I've drawn a cube right here, and it has an area, top and bottom surface area, A, and we're going to give it a height, H. Okay. And of course, the area of the bottom is the same as the area of the top. It's just A. One thing from Archimedes' principle is when we talk about the buoyant force, okay, we know that, let's see, if we have, let's say our object is submerged in a fluid, and for the time being, we're going to use a compressible fluid like water, just for this example. We know that at some depth, D, the pressure at that depth is equal to the density of the fluid, call that rho sub F, fluid, times G times the depth. Okay? Now, we also know that pressure is defined as force over area. So if I know a pressure and the area it's acting on, I can rearrange this to get the force. So this gives us force equals pressure times area. All right, now let's take our box and let me erase this and draw it a little bigger. Okay, so here is our box. All right, just shown in 2 dimensions. It's at the top is at some depth. Okay, its height is H. All right. So what do we have going on? The water pressure, the pressure of the fluid, acts all the way around the box. It acts on the box all the way around. But any pressure this way, okay, is canceled by the same pressure on the other side. Okay, so they all cancel out. The only thing we really are concerned with is the pressure and the force on the top and the bottom. Okay, so if we're just considering the forces acting on our object due to the fluid, otherwise known as the buoyant force, we only have to consider the pressure on the top and on the bottom, because everything else is equal and opposite and it cancels out. Okay, so let's take, let's see, the total force, which we'll call the buoyant force, then is going to equal the force on the bottom pushing up. Okay. Up. Minus the force on the top pushing down. All right. So what is the force in the up direction? It is the pressure at the bottom surface, the pressure here, this pressure times that area. And this force here is this pressure. Pressure bottom, pressure top, times the area. All right. So, and pressure is rho, density of the fluid, times G times the depth. Okay. So what is the pressure pushing up? The pressure pushing up is the density of the fluid times G. Now the depth at the bottom is not just depth D, but it's D plus H, because it's way down here. Okay, times D plus H. All right, multiplied by the area, okay, to give us the force. That's force up. So the force total force, or the buoyant force, is that minus the force down. What's the force down? Once again, it's the density of the fluid times G times, in this case, it's just depth D, because that is the depth. All right, times the area. So we can simplify this. We have rho G times D times A plus rho G times H times A, and the rho G D, it has a rho G D subtracted from it. Okay, so this and all this subtract out, and we're left with F sub B equals rho times G times H times the area that force is acting, that pressure is acting on. Okay, now we have up here, looking at this again, what is the area of the top surface multiplied by the height? H times A is the volume of the object. Okay, so substituting that in, that gives us the buoyant force is equal to the density of the fluid times G times the volume of that object, which is the volume of the displaced fluid. So this is the buoyant force acting on the object. Okay, so let's make a new page. And now we're going to have our object submerged in a fluid again. Okay, we'll draw all the forces acting on the object applied to this object. And let me back up just a bit. I did that for a compressible fluid like water. Okay, but any of the corrections that we would make for compressibility of a compressible fluid like air essentially cancel out. So the same relationships, the same principles, the same formulas hold for compressible fluids as well. So this can apply to compressible fluid like air also, as well as just water. Okay, so every object submerged in a fluid like air has, if it's at rest, it has two forces acting on it. There is its weight pulling down, its mass times G, okay, and it has a buoyant force pushing up. All right. Let me call this W for here, for weight. Now, I'm going to move this over some. There, let's put this over here. All right. So we have the total force then is the sum of the upward force and the downward force. Okay. What is the upward force? It's the force of buoyancy again. And we said that FB equals the density of the fluid, all right, multiplied by G, multiplied by the volume of the object. So the weight of the object is pulling it down. The weight is equal to the object's mass times G. We can also say that mass is the object's density multiplied by its volume, because we define density as mass over volume. Okay, so the object's mass is its density multiplied by its volume. So this is the density of the object. Okay. So its weight is the object's density multiplied by its volume multiplied by G. Okay, so when is the net force going to be positive or upward and this object float up? And when is it going to be negative and float down? Well, it all depends on this ratio. If the ratio of buoyant force over weight is greater than 1, the object rises. If that ratio is less than 1, or FB over W less than 1, the object falls. Okay. Now, let's plug in what we have in our formulas for each of these terms. FB is rho fluid times G times V, and weight is density of the object times G times V. Let me fix that here. Yeah, that was better. Okay. So F buoyancy over weight equals rho of, it's a terrible row, rho of the fluid times G times the volume of the object. The object's weight is rho of the object times G times the volume of the object. Okay, so remember, this is our ratio. This ratio is our criteria for whether the object rises or falls. If you look carefully at this ratio, what cancels out? G over G cancels, V over V cancels, and we're left with the ratio of the buoyant force to the weight is equal to the ratio of the density of the fluid over the density of the object. So right here, this is, again, is the criteria for does it sink, does it fall, does it rise? And it simply boils down to the density of the fluid over the density of the object. But where that ratio comes from is the force balance. Okay, densities aren't forces. They lead to forces when you multiply by G and the volume. Okay, but the ratio of the up force and the down force is equivalent to the ratio of the densities. And this is why Flerfs like to say, oh, well, the density of the object is greater than the density of the fluid, so it falls down. Or the density of the object is less than the density of the fluid, so it rises. Okay, that's where this confusion comes from. Okay, but it's not the density that's pulling it up or down. Okay, it's simply the ratio of the forces applied to the object reduced to the ratio of the densities. So I hope that helps.